K-theory. I will talk about that. For that, I will have to say beforehand, actually, I will have to say a few things about ring spectra, which we call brand-new algebra. So here, I'll try to mention this philosophy that we should be doing homological algebra in this topological setting called spectra. And it's a setting which allows us to generalize a lot of notions from classical algebra to this topological setting. So I'll say a few things about that. And the setting is really essential to talk about algebraic K-theory. And then I'll mention our main results. And I'll try to say a few things about what goes into the proof of our main result. Okay, so to start with the first definition of the degree zero algebraic K-theory group. Let A be a ring. PA here will denote the monoid of isomorphism classes of finitely generated projective A modules, which becomes a monoid under direct sum of finitely generated projective A modules. So you take this monoid, and Grothendieck defines the degree zero algebraic K-theory group of a ring to be the group completion of this monoid. So to clarify what is going on here, let's do the simplest example. If A is a field K, then K modules are just given by their dimension, and direct sum of K modules correspond to addition of dimension. So PK is just natural numbers, right? And then you group complete PK, you obtain that the degree zero K-theory group of a field is just integers. Now later there's a definition of the first algebraic K-theory group due to Whitehead and Bass. It's 1950s. They defined the first algebraic K-theory group of a ring to be the abelianization of the infinite general linear group on that ring. The intuition for this comes from the fact that the first topological K-theory of a space is given by the vector bundles on the suspension of a space. And that's defined using these gluing maps that define the vector bundle. And if you kind of intuitively, these gluing maps correspond to this abelianization of the infinite general linear group on A. The main application of this definition was what is called the Escobordism theorem. It says that if you have a closed manifold of dimension larger than or equal to 5, then the obstructions to triviality of H cobordisms on M lie in this quotient of the first K-theory group of the group ring of the fundamental group of M. And then you quotient it out by the units of the group ring. So here H cobordisms means the cobordisms where the inclusion of the boundary map is a homotopy equivalence, and you say an H cobordism is trivial if it is basically a cylinder on M. And this is a very interesting result because we have this completely topological phenomena, but the obstructions to that lie in these K-theory groups which are defined in an algebraic manner. And this is a recurring thing about algebraic K-theory. It happens to contain important information concerning various fields of mathematics. For example, the second K-theory group was defined by Milner in 1967, and the applications of that was to number theory. At that point, there was a search for a definition of higher algebraic K-theory groups. And the idea was that one should be able to have this higher algebraic K-theory groups, which kind of give us some sort of a homology theory. And it should agree with the second, first, and degree zero K-theory groups that were already defined. And it should behave like a homology theory. For example, if you have an ideal of your ring A, then you would want to have these relative groups which fit into a long exact sequence of this form, right? And actually, there were failed attempts and so for this, but the correct definition eventually was given by Coulomb, which is still accepted as the correct definition of higher algebraic K-theory groups. This definition says that the degree n algebraic K-theory group of a ring A is the degree n homotopy group of this topological space, where we again have infinite general linear group of A appearing in the definition, and B denotes the classifying space, and this plus denotes this plus construction again, which Coulomb comes up with in order to define these groups. It's a construction that takes the space and kills its a maximal perfect subgroup of the pi1 of the space while keeping the homology the same. So it's an interesting construction. And pi n of the space, the degree n homotopy group of the space, gives you the degree n algebraic K-theory of the ring. After this, Coulomb makes several algebraic K-theory computations. One of the important ones is that he computes algebraic K-theory groups of finite fields. And I just showed the final result of that computation here. Actually, Coulomb wins the Fields Medal for his definition of algebraic K-theory and for his computations. But one problem was that algebraic K-theory turned out to be really difficult to compute. For example, Coulomb also tried to compute the algebraic K-theory groups of these rings, which are rings that are defined in a very simple manner. One would expect these to be computable maybe, but actually he fails to compute them, and this is still an open problem. Another interesting connection which shows how algebraic K-theory contains important information while being difficult to compute is the connection of algebraic K-theory with Van de Waal conjecture, which is a conjecture in arithmetics, which I'll not give the precise definition here because it would be too much of a diversion, but it's an important conjecture in arithmetics, heavily studied and still open. And this conjecture turns out to be equivalent to the vanishing of these algebraic K-theory groups. And this is also open still. So I told you how about the definition of algebraic K-theory of rings, but there's also what's called the Walthausen S construction, which allows one to define algebraic K-theory of in this general situation called Walthausen categories. These are basically categories with a meaningful notion of a weak equivalence and a cofibration. And basically through this, one can define algebraic K-theory of pointed model categories, topological spaces, differential graded algebras, ring spectra, and so on. So actually, Walthausen's initial application was to topological spaces and manifold topology. So I'll start saying a few things about ring spectra because this is so fundamental to the study of algebraic K-theory. But let's start with spectra itself, and then we'll get to ring spectra. So the category of spectra, vaguely speaking, can be considered as a category obtained from topological spaces by inverting the suspension endofunctor on topological spaces. So this is something like a localization of a category. So just like the way you have, say, a map from a module to its localization, there's a functor from topological spaces to its localization, which is the category of spectra. I guess it would be easy to, one could say that this is the category of spectra is the main setting for stable homotopy theory, and the objects in this category are the main objects of study in homotopy theory. And I guess one way of looking at this is that spectra is a category that captures a lot of the complexity of topological spaces, while being easier to compute. And but while being more computable and being more algebraic. In various, it's more algebraic, it's closer to homological algebra in various ways. For example, there's a notion of triangles in spectra, or fiber sequences, co-fiber sequences in spectra, which generalize the notion of short exact sequences of chain complexes, or short exact sequences in the classical sense. Spectra happens to be a linearization of topological spaces in a certain way, in the sense that homotopy class of maps between two spectra is an abelian group, where in topological spaces, homotopy class of maps between spaces do not have to be a group or an abelian group at all. So it's somehow, in that sense, it linearizes topological spaces. And if you have and we also have a notion of homotopy groups defined for spectra too. If you have a spectrum, then we have a homotopy group. So such a spectrum is defined for each integer I. So compared to topological spaces, you also have these negative homotopy groups. And each of these homotopy groups are abelian groups. Compared to topological spaces where pi 0, pi 1 doesn't have to be abelian groups, but in spectra things are a little bit nicer. An important fact about spectra is that spectra represent cohomology theories in spaces. For example, there is this spectrum called the Lambert-Mclean spectrum, which is a spectrum defined by the property of, it's uniquely defined by the property of having all its homotopy groups to be given by the integers concentrated in degree 0. So the rest of the homotopy groups are trivial. So this is analogous to Lambert-Mclean spaces, basically. It's the spectrum version of Lambert-Mclean spaces, but we consider this in degree 0. So there is a spectrum, and if you have a topological space U, then the degree I cohomology of that space is the negative I homotopy group of the mapping spectrum between the suspension spectrum of U into the Lambert-Mclean spectrum. So this is why we say the Lambert-Mclean spectrum represents ordinary cohomology theory. And the interesting thing is that for every spectrum, you obtain a cohomology theory in topological spaces, and for every cohomology theory, there is a spectrum that gives that cohomology theory. And one thing to keep in mind is that when we think about algebraic K-theory as a structured object, as a spectrum, basically, rather than just considering these groups, algebraic K-theory groups, for a given ring spectrum over space, Kx would be considered as a spectrum whose degree n homotopy groups are your algebraic K-theory groups. So we kind of think about more structures and topological structures on algebraic K-theory rather than just considering the groups. Okay, so I was saying that spectra is in certain ways closer to algebra, in the sense that we can, one of the reasons for that is that we can define all these classical notions in algebra, also we can define them in spectra too. And one thing that aids this is the fact that there are models of spectra that are symmetric monoidal, in the sense that there is a smash product on spectra, which basically comes from smash product of topological spaces, actually. And this smash product behaves nicely in the sense that it's associative and unital and symmetric. So it's a symmetric monoidal category. That's what it's called. The correct analogy, although this smash product comes from topological spaces, actually the correct analogy to compare this with is the tensor product in abelian groups. Like philosophically, in many situations, this smash product functions the way tensor product functions in abelian groups. For instance, we can define a ring spectrum, a ring object in spectra in this way, we can say a spectrum is a ring spectrum if there is a map from X smash X, which basically is the ring multiplication map, which satisfies certain associativity and unitality conditions. So these associativity and unitality conditions would also be given by these diagrams. So it's defined in a categorical manner. And the idea is that this is how you could define a ring in the classical sense too. You can say a ring is an abelian group for which there's a map from R tensor R to R, which satisfy associativity and unitality, right? It's a bilinear map. So that's the way one takes a lot of these like classical notions in algebra and realize them in spectra. You just take the classical notion, replace all occurrences of the tensor product, and with the smash product of spectra. The categorical way of saying this is that a ring spectrum is a monoid in the symmetric monoidal category of spectra, basically. And in a similar way, one can define commutative ring spectrum, modules over a commutative ring spectrum, algebras over a commutative ring spectrum, and so and so. The main example maybe we should think about, at least for the purpose of this talk, of a ring spectrum, is that if you give us a classical discrete ring R, then HR, which is again the spectrum defined by the property of having all its homotopy groups to be concentrated in degree 0 where it is given by R, this spectrum is a ring spectrum. And if R is commutative, this is a commutative ring spectrum. And it's kind of interesting that, vaguely speaking, through this construction, ring spectra contains rings, the category of rings, as a full subcategory. So basically, spectra sees all the information about classical rings in itself. So ring spectra generalize classical rings in that sense. And one can think about K-theory of this ring spectrum HR as a ring spectrum, and as expected, that turns out to be equivalent to the K-theory of the ring R, defined in the sense defined by Coulomb. So that it's kind of like definition of K-theory is compatible with the classical definition. Okay, I was telling you that our main results are computations of these algebraic K-theory groups of differential graded algebras, right? And for that, I need to, I want to start by defining what a differential graded algebra is. So a differential graded algebra is basically a chain complex, where a chain complex is just a chain of abelian groups with morphisms between them, where the morphisms have to compose to 0. So this is the information of a chain complex. For it to be DGA, it has to have a multiplication, associative and unital, that works with the grading in this way, which means that if you have a degree I element, j element, they multiply to degree I plus j. And the differentials have to satisfy the Leibniz rule. So this here is the information of a differential graded algebras. And homology, as usual, it's given in the usual way. Degree I homology is the kernel of the map coming out of degree I, portion to that by the image of the map coming into degree I. So what are examples of interesting DGAs? If you take the cochain complex of a topological space U with the cup product, the usual cup product, this is a differential graded algebra. Cup product is associative and unital. And this, I'm guessing, is historically the first example of a differential graded algebra. Another example to think about is that if you take a ring, you can think about it as a chain complex that's concentrated in degree 0, right? Place it in degree 0 of a chain complex and then make everything else trivial. Then that's also a DGA in a canonical way. So in that sense, DGAs generalize rings too, just like ring spectra. There's one more example to think about here. If you take a graded ring, right, And then you can think about this grading with respect to the chain grading. So degree I graded part of this A would be the degree I part of the chain complex, and then impose trivial differentials on that. And that also becomes a DGA. So in that sense, DGAs also carry all these like graded rings too. And the homology of such a DGA, because all the differentials are trivial, is also A star. Such DGAs where the differentials are trivial, are called formal DGAs. Okay, so I would say like the formal DGA corresponding to this graded ring. It's just like impose trivial differentials. That's what it is. Okay, so I was talking about how ring spectra contains generalized many things from homological algebra. One thing is that ring spectra generalize differential graded algebras. To make this precise, there's this theorem of Stanley and later improved by Shipley, which says that the homotopy category of RDGAs is equivalent to the homotopy category of HR algebra. So HR is the ring spectrum, you take algebras over it, so this comes from spectra. Homotopy category means the category you obtain by inverting homology isomorphisms. So, the way you think about chain complexes up to maps that induce homology isomorphisms, you also think about DGAs up to maps that induce homology isomorphisms. So you invert those homology isomorphisms and you obtain this homotopy category, which kind of philosophically contains the information you really care about. And similarly, in spectra, we have weak equivalences. These are maps that induce isomorphism in homotopy groups. And the homotopy category becomes the category you're really interested in certain ways. This equivalence is actually stronger. It's an equivalence of model categories. So there's a zigzag of equivalent equivalences of model categories if you like. So for homotopy theorists, these are pretty much the same thing. So RDGA is often pretty much the same thing as an HR algebra. All the homotopy theoretically interesting information about RDGAs equivalently appear in HR algebras. There is a forgetful functor from HR algebras to ring spectra. I mean, if you have an algebra over a ring, those algebras would forget the rings. And such a forgetful functor tells us that the way DGAs generalize rings, ring spectra generalize DGAs. So that's an interesting fact. Now I can talk about these trace methods, which I was telling that it's a program that was developed to compare algebraic K-theory with more computable homology theories. So the idea is to boil down algebraic K-theory computations into computations of more computable homology theories. And the main theorem of this program, trace methods, is this one, which says that if you have a map of connective ring spectra where the degree 0 map is surjective with a nilpotent kernel, then there is a homotopy pullback square where TC here denotes topological cyclic homology, which is something I'm going to define in a little bit. So there's this pullback square. So let's stop and before I define TC, and so let's see what this pullback square is giving us. So the idea is that, let's say you have a map of this form. This is saying that if you know the TC of B, if you know the K-theory of B, right, in order to obtain K-theory of A, you just need to compute TC of A and understand this map. Then you just take the pullback square and that gives you the K-theory of A. So it basically reduces K-theory computation into a topological cyclic homology computation. This is often applied to the case when you start with a connective ring spectrum. Oh, I forgot to tell you what a connective ring spectrum. So a spectrum is connective if all of its negative homotypic groups are trivial, and all the spectra I'm going to talk about will be connective. This is often applied to the case when you start with a ring spectrum, connective ring spectrum, and you map it. You basically kill all homotypic groups above degree 0. Basically, you take the degree 0 Postnikov section, and you obtain this Lambert Mclean spectrum. So B is often of this form, in which case K-theory of this is just K-theory of this classical ring pi 0 of A, and TC of B is just the K-theory of, TC of this classical ring. So in order to define TC, I need to define topological Hochschild homology, and which is again actually a homology theory that was defined in order to be able to define TC, in order to be able to study K-theory. So that's why this is such a huge program, trace methods. But before that, there was already a classical notion of Hochschild homology from homological algebra. So let's start with that. So given a discrete ring over a field K, Hochschild homology of that ring is defined to be the homology of this chain complex, where in degree 0, this chain complex is just A, and then the second tensor power of A, third tensor power of A, and so and so. And these differentials B, so B's, are given as this alternate sum over DI of, now where DI multiplies the adjacent elements, the AI and AI plus 1, and for I less than n. And dn makes this funny thing. It applies a cyclic permutation to these elements by moving A0 to the right, A1 to the right, and then an all the way back to the beginning, and then multiplies the first two factors. So it works in this way. And the homology of this chain complex becomes the Hochschild homology of A. Now to make the topological version of Hochschild homology, again, one applies the same idea. Just take the previous definition, replace all the occurrences of, start with the ring spectrum and replace all the occurrences of this tensor product with smash products. That's the first thing you do. But in this case, instead of having a chain complex, we need to consider what's called simplicial spectra. The reason for this is the following. Spectra is not an additive category, so it's not really meaningful to talk about. It's not really meaningful to talk about chain complexes and spectra. You can't really talk about it. But instead, we have these simplicial resolutions. And simplicial objects, and this is kind of one way to see the analogy here. A chain complex is what you use in classical algebra to have your nice replacements, to have your projective resolutions, right? In topological spaces, you have your nice replacements by taking CW complex approximations, right? You replace a topological space with a CW complex, and that would be your nice resolution. So you get a cellularization of your space. So simplicial objects do pretty much a similar thing, in the sense that you think about this degree 0 part as the spectrum of 0 simplices, degree 1 part as a spectrum of 1 simplices, and so and so. And then these face maps here tell you how you attach these simplices. That's kind of the idea. And the face maps correspond to these DIs in here, where, for example, the first map here would multiply the adjacent elements, the second map here multiply the second adjacent elements, and the third map applies a cyclic permutation and then multiply, and so. And and then you can apply a realization functor to a simplicial spectrum, which basically takes all these 0 simplices, 1 simplices, 2 simplices, and attach them together according to these maps. That's kind of what it does. And THH is defined to be the realization of this simplicial object. And then the homotopy of the realization becomes the topological Huxley homology condition. This is kind of how you the analogous thing for chain complexes in spectra are the simplicial objects, and then the homology of the chain complex corresponds to taking realization and then taking the homotopy groups in this way. So this definition is actually due to Buxted, which was a very difficult definition to make back then because these smash products of spectra were not available at that time, which is a relatively modern new construction. And Buxted makes this definition, and he computes the topological Huxley homology groups of HFP. And this is a very interesting and a very important theorem. One reason for that is because these THH groups turn out to be very simple. Because a priori, these groups depend, as you take smash products in spectra, you take smash products over the sphere spectrum. So smash products in spectra a priori depend on stable homotopy groups of spheres. So these THH groups depend on stable homotopy groups of spheres. And all these smash products are actually give you really huge results in general. But kind of magically, these THH groups turn out to be really simple. And that's why this theorem is one of the important results in trace methods. And I want to note that this THH turned out to be, it is at the same time a formal DGA, and we compute the algebraic K-theory of this. So one reason we compute algebraic K-theory of formal DGAs, one of our main motivations, was to compute the algebraic K-theory of THH of HFP. Okay, to define topological cyclic homology, I need to talk about even more structure on THH. There's a circle action on THH that comes from the fact that you have this action of cyclic group of order n at degree n stage of the simplicial object defining THH of a ring spectrum. So in degree 0, you get a cyclic action of order 1, which means no action. In degree 2, you have a cyclic action of order 2, which just switches these two factors and so and so. And this turns into an S1 action on THH of X. And that's where the word cyclic comes from in topological cyclic homology. And a little more before defining TC. If G is a finite group and E is a G spectrum, there is this notion of Tate construction, with respect to G for E. It's defined as a co-fiber of this normalization map from the homotopy orbits to homotopy fixed points. And co-fiber sequences, as I was saying, are like short exact sequences. So this is kind of like completing this map to a short exact sequence. So thank you. Very vaguely speaking. This normalization map, if you're wondering where this is coming from, if E was a discrete G module, then there's a map from orbits to fixed points given with this formula. One can easily see that this sum is invariant under the action of G, so it lands in fixed points. And one can make sense of this for spectra and obtain a map of this one. So one more piece of structure we have on THH is what's called the Frobenius Map, which is a map from THH of X to the Tate construction of THH of X for every prime P with respect to CP. So THH has an S1 action, CP is a subgroup of S1, so THH has a CP action. And you can take Tate's constructions with respect to that. And with all this at hand, now I can give you the definition of topological cyclic homology of a ring spectrum. For the particular case, when we're looking at the ring spectrum corresponding to an FPDGA. Okay, so this is the case I'm going to give the definition form. In the general definition, you have to consider all primes, so it becomes a little bit more complicated. But often one reduces by localization techniques, one reduces to this case where you only need to consider one prime CP, one prime P in this fiber sequence. So with the so with this theorem TC of the ring spectrum corresponding to this an FPDGA is given to be the fiber of this map. Again, this is like completing to a triangle. So whenever you have a map, you can define its fiber. Is the fiber of this map where this part is the homotopy fixed points, and this part is the homotopy fixed points of the Tate construction. The map phi p HS1 denotes the map that we obtained from phi p by applying the homotopy fixed points functor, and Ken is the map that you obtain by identifying S1 fixed points as first taking CP fixed points and then S1 fixed points. And you always have a map from CP fixed points to the Tate construction, because just from the definition of the Tate construction, so you always have this map. So this is equivalent to this, and then you can map canonically into here. So that gives you the canonical map. And the fiber of this map is this TC of HS. Now, actually, there's more history to this. The original definition of topological cyclic homology is due to Hsiang, Böckstedt, and Knudsen in 1991. And only very recently, Nicolas and Schulze gave this much simpler definition of topological cyclic homology, which really gave an improvement to the computations. It kind of like made it easier to compute topological cyclic homology and therefore algebraic K-theory. And we make use of this definition in our work for our computations. Okay, now I can state our main result. So I will state our result for this particular formal DGA. So here FPX2 denote the graded ring given by the polynomial algebra with a single generator in degree 2. This is a graded ring. We can imagine this as a formal FPDGA. So when I write this, I mean the formal DGA corresponding to this graded ring. So we just impose trivial differentials to this graded ring and imagine it as a DGA. And this is our result that basically gives the algebraic K-theory groups of this formal DGA. Here, WRFP denotes the big width vectors of length R in FP. These are basically taking big width vectors on a commutative ring is same as is basically taking the co-real lambda ring on that commutative ring. And looking at this result, so the even algebraic K-theory groups turn out to be trivial, and the odd homotopy groups are given in this way. So this part just comes from the algebraic K-theory of FP. Remember, that was Coulin's computation that I told in the beginning, that he compute algebraic K-theory groups of fields, and that's where this part comes from. And this part is really the new thing that comes from our computations. It is pretty interesting because, I mean, this result looks kind of interesting because the final result, because it's actually surprisingly simple. If you look at the other computations in the literature, the previous similar computations, you see that the final answers are not as compact, as simple as this one. So this part kind of always appears. So the new parts just have a very compact and simple description. It's interesting.
Yes,
yes.
So was I in the exponent of P?
Here?
In the second summon, yeah?
Yeah.
So that I, what's it? I mean, it's not related to the dimension of the K-theory group, or?
Oh, that should be R. Sorry.
I see.
I is R.
Okay.
Yeah.
Okay. So could you also recall a little bit of what's the width vectors here? Isn't width vectors something similar to that also?
Yeah. So these width vectors, they are basically the Coffey lambda rings on a commutative ring. So kind of these lambda rings are rings with some sort of a Frobenius on them, and so on.
Okay.
Yeah, but the lambda rings, I mean, sorry, the big width vectors here appear in a from the combinatorics of our computations. They don't really come from some sort of a conceptual place. They just
well, I
pop
had the
up
idea that the width vectors are something like the p-adic numbers in this case, or
yes. Well, if you do the like small width vectors, then the small width vector, the usual width vectors on FP are just p-adics, right?
Okay, thank you.
But you take various products of them. Yeah. We also do computations of various other formal DGAs with polynomial homology in different degrees and exterior algebra homology and quotients of the polynomial homology. These are kind of like some of these are generalizing classical algebraic K-theory computations to formal DGAs. Okay, one interesting application of this result is to the fundamental theorem of algebraic K-theory, which is due to Coulomb. It says that if you have a Noetherian regular ring R, regular here means that the projective R has a finite global projective dimension. If you take such a ring, then the algebraic K-theory groups of the polynomial algebra over R are same as the algebraic K-theory groups of R. This is pretty interesting because, I mean, algebraic K-theory groups often being so difficult to compute. In this case, it gives a very, simple answer. And one thing to ask, I mean, keeping all these things I said about DGAs in mind, one natural question to ask here is to ask whether we can replace this with a formal DGA with polynomial homology, right? If this was a formal DGA with polynomial homology with a generator, in this case it's in degree 0, but what if we put the generator in a place that is other than degree 0? And that's exactly what we do, right? So we compute the algebraic K-theory group for this DGA with polynomial homology, and we show that this is not same as the base field. So if you go back again, this is the algebraic K-theory of FP, and then this is the extra part that comes and which shows that this is not same as, these groups are not same as the algebraic K-theory of FP. So this is basically showing that the fundamental theorem of algebraic K-theory do not generalize to formal DGAs with polynomial homology. Okay, so to say a few things about one thing that goes into our computations is this notion of a graded ring spectrum. It's basically, you can just take the classical notion of a graded ring and replace all occurrences of coproducts of, modules with coproducts of spectra, as shown in here, and just define the same thing by replacing the tensor product with smash product of spectra, which you would impose the multiplication to some degree I part and degree j part of the splitting to the degree I plus j part, just like in classical notion of graded rings. And finally, you would ask the unit to lie in degree 0. This is what the last statement says. So this is the notion of a graded ring spectrum. You can define the notion of a graded ring spectrum in this way. And we have this theorem from one of my previous works, which says that if you have a connected formal RDGA, whose homology is nice in the sense that the homology is a monoid ring. So it's nice in the sense that the homology is a monoid ring, which happens to be the case in most of the rings we consider in homotopy theory. Then the ring spectrum corresponding to such a formal DGA satisfies the splitting. It can be represented as HR smash E, where E is a graded ring spectrum in a non-trivial way. Now this provides two things. It provides a splitting, and it provides that this E is a graded ring spectrum. And actually just the splitting itself says that the THH of computing the THH of such a ring spectrum just boils down to the computation of the THH of the base ring, which you often know. For example, R is FP in our situation. And the computation of the homology, Hochschild homology of the DGA. So this is a completely algebraic thing to do. Actually, even because A is formal, the spectral sequence that computes this has all trivial differentials and so on. So this part is really, really computable, and this part is often known. And this theorem basically says that for a formal DGA, you can often, in many cases, you will be able to compute the topological Hochschild homology. And one more thing I was saying is that we also have a graded ring structure in here, right? So let me say a few things about how that graded ring structure here play into our THH computations. What the graded ring structure does is that it splits THH as an S1 equivariant spectrum into a coproduct. This is a generalization of some of the ideas used by Hesse-Hald and Madsen for computation of the algebraic K-theory groups of truncated polynomial algebras, where they were using similar ideas for basically classical rings. To compute THH of classical rings, we generalized to graded ring spectra, basically. We show with Tassos Molinos that THH splits for graded ring spectrum. And how does this splitting occur? If you have a simplicial, so we have this simplicial spectrum whose realization is THH, right? And X splits in this way into a ring spectrum. And what you get is that because smash products commute with coproducts, if you take the coproducts out of each smash factor, you obtain this giant coproduct, right, on the S+1 smash power of X. And then each cofactor here is obtained by focusing on the cofactors where the sum of the indices is equal to I. Okay, so the I summand is obtained by just taking all these cofactors where the sum of the indices is equal to I. One can easily see that this is closed under face maps, because face maps multiply two factors, right? If you multiply these two, it lends in degree I1 plus I2. So the face maps preserve the sum of indices, right? Because it multiplies. And then degeneracy maps do the same. It's pretty immediate. And then actually S1 action is also this is also invariant under the S1 action, because if you apply cyclic permutation to these elements, the sum of the indices will not change, right? You just switch the order of these indices, their sum doesn't change. So each BXI we obtain is a simplicial spectrum. So you obtain a splitting of the simplicial spectrum whose realization is THH of X. And this also respects the S1 action and therefore we obtain an S1 equivariant of THH. And what does this? How does this feed into topological cyclic homology computations? Well, often in this situation, not always, but often obtains a splitting of. So recall that TC is defined to be the fiber of this map, and the previous splitting gives us a product splitting at the second and third parts of this fiber sequence. The reason for that is because this coproduct happens to be a product at the same time in the cases of interest. This is often the case in spectra because coproducts and finite coproducts and products agree in spectra, and sometimes infinite coproducts and products too. So we have a product splitting of THH, and because taking homotopy fixed points is a limit, it commutes with product splittings. So you get a splitting in here and a splitting in here in a similar ways, which also gives you a splitting of the, for example, homotopy fixed point spectral sequences computing these things and so on. So it really simplifies the computations in that sense. So these parts split, but topological cyclic homology don't necessarily split because this map, the Frobenius map, do not respect this graded splitting. Because this Frobenius map, it's like the classical Frobenius map that takes the p-th power, right? If you take a graded ring, take the p-th power of an element, that doesn't respect the grading. And similarly, this Frobenius map somehow takes the p-th power, and therefore it doesn't really respect the grading either. So this TC doesn't split, but we still have a hold on how this Frobenius map behaves with respect to splitting, with respect to the splitting of THH2. It just multiplies the degree by p, just like the Frobenius map would do in the classical graded setting. So that's so we get a hold on to this map, and we get a hold on to each homotopy fixed point factor, and then the rest of the proof basically goes through spectral sequence computations for to compute all these factors. Yeah, so this is where I would like to stop, actually. 54 minutes.
Okay, thank you very much, Asgur. Congratulations for your talk.
Yeah, thank you.
Now we can open a turn of questions. So you can raise your hand or just open your microphone. If you have a question or whatever, comment.
I have a question,
yes.
I can ask it. Yes, so I was wondering what sort of framework you're working in here. You didn't say anything about whether you're using orthogonal spectra or infinity categories, or what sort of model of spectra are you using when you're doing this work?
Yeah, it's interesting. So most of the things take place in infinity category of spectra as much as we can. Mm-hmm. But when we are showing that this thing is graded ring spectrum, we kind of needed to have an explicit description. We want to have that coproduct and the way maps work. So we had to have some kind of rectification results, which kind of show you that these graded spectra in symmetric spectra, basically. Okay. These graded symmetric spectra give you the graded.
So you're working in both symmetric spectra and infinity categories then, and trying to.
Yeah. So you start with symmetric spectra where you can really write these maps for graded ring structure. Right? If you take the free thing, you see this thing. And then that gives you a graded ring in infinity category. But I think nothing else really takes place in the setting of infinity, outside the setting of infinity category.
Okay. I also have another question.
Yes.
So most of what you're doing is basically like computations with spectral sequences. Is that correct, or do you have?
Well, there is one important part here, which I actually didn't mention because I was trying to give a white background. But so there is an important part of this work, actually, I completely skipped, where we provide a new identification of THH. THH of FP as an E2 algebra. And maybe I'll try to share that on my screen now.
Okay.
So let's say stop sharing. Okay, now you should be seeing my
Yes, I can see
screen.
it.
So yeah, we have this theorem 1.3, which is one of the important inputs that go into the computation, which I actually is an interesting. We see it as an interesting result. So we show that THHK is K-smash the loops on S3 as an E2 algebra. So this equivalence is somewhat obvious as an E1 algebra, because this is just the free thing and this is the free thing, right? But it's kind of interesting. There's a group structure on S3 that comes from quaternions, right? So it's an E1 algebra. You loop it, it becomes an E2 algebra. So kind of like a little surprising that this thing is an E2 algebra, right? So you have this E2 algebra structure in here, and does it agree with the E2 algebra structure in here? Right, that's an obvious question to ask. And we show that it does agree.
Okay.
So that was one of the things, important stepping stones in these computations. We show this using Bastera and Mendel's EK obstruction theory. And that's important because in the spectral sequences, like in the Tate spectral sequences, so one needs to use, one needs to have one wants to have this algebraic structure, right? You want to know the algebraic structure in the Tate spectral sequence and the fixed point spectral sequence. So if you take the THH of THH, right, you need to know the E2 structure in here so that you obtain the E1 structure on THH of THH. So we obtain the E1, so this becomes an E1 splitting after taking THH, because we have an E2 splitting.
Is this entire work that you're doing, is that connected to, because it looks like you're taking, you're really saying that you're taking iterated THH, and it also looks like that's sort of what you're doing when you're doing the K-theory as well. You're doing like iterated K-theory of FP, right, sort of in some way.
Yes, there is some sort of a connection. Again, I can scroll down in the paper. So there is a connection, actually. So it's actually part of the application work. So we calculate K-theory of THH of FP, right?
Yeah.
So you have this sequence of maps that come from trace methods. And we actually compute also this part, K-theory of TC of FP.
Okay.
That's somewhat easier. We use Hopkins-Miller obstruction theory and show that this thing is actually formal as an FP algebra, as an FP DGA. So that's another like formal DGA, formality consideration for DGA. So this is formal as an FP DGA, and the co-chain complex on S1, sorry, ZP DGA. Formal as a ZP DGA. The co-chain complex over S1 is also formal as a ZP DGA, and so we deduce that the K-theory of this is the same as the K-theory of this, which is due to Antiu, Heller, and Gepner, I think.
Yeah. I know they wrote a paper at least.
Well, it should be them then. This is same as the K-theory of the coefficient ring, K-theory of C. So we basically have a complete identification of K-theory of K-theory of FP to K-theory of TC to K-theory of THH of FP. Okay. And it's interesting that we kind of like argue quickly how there might be interesting things going on here. Might be. So it's one of the small applications of this.
Good. Thank you for all the
answers. Yeah, things I didn't have time to cover, but I wanted to cover. So I was happy that you asked this question.
Okay, any more questions? If anyone else has a question, please open your microphone. Unfortunately, the chat doesn't work currently. Well, I had one very technical one, I guess. Could you share the other tab, maybe your slides?
Okay. Yes.
I was wondering, so I guess that those coproducts, infinite coproducts, turn into products because these the factors, the connectivity tends to infinity or something like that. Yeah, and the canonical map must go from the ith part to the I part, right?
Yes,
from the left
it
to the right.
Like that.
Yeah, this somehow resembles, it's not, right? Because the factors on the right are different from the factors on the left, but this resembles the definition of a homotopy limit, doesn't it? As homotopy limit is the homotopy fiber of a similar map. I don't know if there is any relation. So TCX is not exactly a homotopy limit because you have different objects left and right. But have you used anything like that to make the explicit computation, or?
No, it never occurred to us. Yeah, you can define a homotopy limit that way, and does this somehow? Can this be turned into homotopy limits through that?
Yeah, the thing in a homotopy limit is that you have the two maps. One of them is diagonal; it's essentially the identity, and the other one is it goes from the ith part to the I+1 or I-1 part, whatever.
Yeah.
But in this case, it makes a jump, so I'm not sure.
Yeah, but that's not a problem. Actually, you can even parse it into further pieces. Mm-hmm. You can parse this into pieces where it does that. So that it's homotopy limit of these factors. Yeah, it's interesting. I would have to look at it, but it's interesting. But I never thought about it. But you don't have the same thing on the left and the right, so that's kind of one of the things.
Yeah.
But it might be somehow
some relation, maybe, I don't know.
Yeah, maybe. Yeah, that's interesting. I don't know.
Yeah, my other question, I think you already answered when you showed your paper. It was whether, your main theorem, if you can put it here in the screen.
Main theorem? Okay, let's do that.
Yeah, well, I don't know whether you called it main theorem or anything like that. It was your theorem with your collaborator.
The calculation of THH.
Of K-theory?
Yeah, so this is, you want the older, oh, sorry, you can't see on my screens.
I think it's later. Yep, before. There it is. Yeah, great. Yeah, I found it as far as I've understood from when you showed your paper, this theorem is actually true for perfect fields of characteristic P, isn't it?
Yes.
And you replace the second factor and the FP on the right with the corresponding field.
Yeah. The thing is that go ahead. Yeah.
No, so in some sense you already give a fundamental theorem of K-theory in this context, right? For perfect fields and one variable in some degree.
Yes.
And can it be improved? Can you, I don't know, remove some hypotheses on FP? Maybe a non-perfect field or some algebra over a perfect field?
Yeah, well, actually, perfectoid rings, right? That's kind of the obvious thing to consider these days. Yeah, that's a project we consider working on with Tassos, doing the same thing for perfectoid rings. But somehow, like, the spectral sequence considerations get stuck at certain points. But in similar situations, people were able to get away with it by considering some topological considerations, while taking fixed points. So we do hope that one could be able to do the perfectoid version of this one too. But we started working on other things.
Yeah, well, I like very much spectral sequences, but I don't know, maybe you can do things in a different way.
Yeah. I mean, the goal is to get rid of spectral sequences.
Or maybe you can adapt the spectral sequences to this other context. I'm not very much acquainted with perfectoid rings, so I don't have anything to say there.
Yeah, so you're saying if you think about like a general algebra over a perfect ring, and so is that what you're saying?
I don't know. Maybe I was thinking some, I don't know, local FP algebra, regular, who knows?
Yeah.
I like say, what about replacing FP with a polynomial ring itself over FP, or I mean, power series ring? Don't know.
Yeah. I mean, definitely, there should be generalizations of certain kind.
And have you tried, for instance, here an iteration? I mean, so what would happen with this example, but with two variables?
Yeah, that's also interesting. That's part of our part of mine ongoing work to generalize these results on to DGAs with formal DGAs with various rings, various homology rings. That's an ongoing project that we didn't go through. Like, I didn't go through every detail, but yeah, tensor products of things. Because in that case too, you still have these graded rings and the smash product splitting I showed in this part still works. This kind of things work, so that's definitely possible. But
okay, thank you. Is there any more question? You can raise your hand or open your microphone. Well, Oscar, there seems to be no more questions, so I would like to thank you again for your talk. It's been great.
Yeah, thank you very much for it was a pleasure.
Okay, so we'll see each other. Anyone interested next week? It will be on Tuesday. Thank you very much. See you.
Thank you. Bye.